Okay. Hello everyone. Again, my name's Brian Jackson. I'm a PhD student at Stanford University. Super excited to be here. This is my first time at JuliaCon. Already learned a lot, and definitely looking forward to learning more from you guys in the next couple days. Oh, I unplugged it from there. I'm supposed to.
You need to use this one.
Oh, got it. Okay, cool. All right, waiting for it to come back up. There it is, except that's my view. Let's try that again. All right, so today I'll be talking about some of the recent research that I've been doing with my colleagues in the Robotic Exploration Lab at Stanford on porting trajectory optimization to Julia. So before we talk about what trajectory optimization is, I want to first talk about why we're trying to address this problem in the first place. This is maybe one of my favorite videos of why controlling robots is hard. This was 3 or 4 years ago at the DARPA Robotics Challenge here in the US. And these were state-of-the-art robots at the time, and they just have a really hard time doing basic locomotion tasks. So robot locomotion is still a very much open and unsolved problem. And so our goal in the Robotic Exploration Lab is to endow these more complex robotic systems with behavior that is more dynamic, agile, and intelligent. And our approach for doing so is with trajectory optimization. So as a brand new lab at Stanford, we started developing a lot of new infrastructure, and part of that infrastructure is this new package, TrajectoryOptimization.jl. So before we talk about what the package is and kind of what it does and what trajectory optimization is, I want to talk about why we picked Julia, especially when nearly everyone in the robotics community is using languages such as Python or C++ or MATLAB. So all of these reasons should be very familiar to you. The ease of use was a high one. In particular for us, it was the linear algebra syntax, which is just beautiful and made the algorithms much faster to write and to develop. And maybe more importantly, it makes the algorithms more transparent and easier to read. Making this transfer from what we write in our papers to what you see in the algorithm and making it re-implementable much more realistic. Obviously, the speed of Julia was a big one for us since we were competing against solvers written in C++ and Fortran. And last but not least, we found multiple dispatch to be kind of a very natural format in putting together a code base fundamentally rooted in the concepts of optimization and mathematics. So some of the key features of the solver, we kind of work in a plug-and-play solver where you set up your problem and then you use a solver, any of the solvers that we have implemented to solve it. And then we also theoretically can set up and solve in about 40 lines of code-ish, so we kind of make it easy at a high level to put these things together. We also try to make it so the core algorithms are transparent, and we also ship it with a suite of canonical problems and benchmark problems. We interface with a lot of the amazing work done by the Julia robotics community, along with interfaces to IPOpt and SNOPT and anything else that uses the MathOpt interface. And of course, we use forward diff because it's amazing. So now that we've talked about this term several times, let's actually talk about what trajectory optimization is for those of you who may not be familiar with it. So at its heart, trajectory optimization is an optimization problem, of course, but it's in particular focused on systems that have dynamic behavior. So we have some system that's at some initial state. We want to get to some final state while minimizing some objective function. This objective function could be a function of safety, fuel efficiency, time efficiency. But kind of very important, we subject this optimization problem to the dynamics of our system, which this kind of inherently makes it non-convex and non-linear. On top of all this, we can impose additional constraints such as obstacle avoidance, monetary budget, fuel budget, workspace limitations. We can all put this in this framework, which makes this problem of finding the sequence of controls on our system that kind of drive us from our initial state to our final state kind of very non-trivial. And this is the field of trajectory optimization. So while our emphasis in our lab is mostly on robotics, it's important to point out that this works on much more than just robots. So while robots can do awesome behavior like the Atlas robot at Boston Dynamics, this also applies to perhaps optimizing power production in order to meet demand, controlling chemical productions, planning spacecraft or trajectories for spacecraft, or with all the recent talk in pharmaceuticals, this works for similar behavior where we're trying to control a system to achieve some desired output. Also, important disclaimer, we can often do better than this if your dynamics have a particular structure, as in, for example, if they're linear or fully actuated. Trajectory optimization is kind of the most general framework you can work within, but that also gives it a lot of power at the same time. So now that we've kind of set up this problem, how do we actually solve these optimization problems? So typically, kind of the standard state-of-the-art methods it's referred to as direct collocation, where you take all of this, the decision variables of your states and your controls, pass them off to a nonlinear programming solver such as SNOPT or IPOPT, and it gives you back a solution doing all of its magic. And while this works on a wide variety of systems, and particularly works really well in robotics, it comes at pretty high computation cost, where on simple benchmark problems can take a couple seconds to a couple minutes, whereas more complicated solutions can take on the order of hours to running overnight for high dimensional systems. So our question in our lab was, can we do better than this? Can we put together a solver that leverages the structure and reduces this runtime? And the result is TrajectoryOptimization.jl and our novel new algorithm called ALTRO. So by leveraging the structure of the problem, we got pretty good speed ups in terms of runtime. We typically got on the order of 2 to 10x in speed ups in terms of computation time. And in addition to runtime, we also meet the same constraint satisfaction, which for us is perhaps more important in the field of robotics than kind of finding the truly optimal solution. So what are the types of problems that what are the types of problems that we're trying to solve, and how are we doing it? And before we talk about those, I want to note an important kind of shift in the paradigm that TrajectoryOptimization.jl and ALTRO kind of bring to the table of this field. So previously, a lot of communities, whether they be research or kind of commercial, had a particular solver, a particular method for solving these problems, and they kind of smushed their problems in order to work with that particular method, whether that be DDP or direct collocation. But now with TrajectoryOptimization.jl, all of these things live under the same roof, and with the power of multiple dispatch and the generality of Julia, makes it very easy to plug and play with your different pieces of different algorithms in order to get kind of a custom-made solver for your particular problem. This is exactly what ALTRO is. We took a little bit of augmented Lagrangian with ILQR and then tacked on some kind of projection stuff at the end, and voila, we got state-of-the-art performance. So these are some of the problems that we're working on. So all of these problems kind of share the same trait in that trying to solve this type of problem with a general purpose off-the-shelf solver where you don't have access to the guts of the solver would be very difficult, where we're able to leverage like the power of ADMM, which is a parallel process, to do a quadcopter team lift, or solve bi-level optimization problems for doing game theoretic approaches to drone racing. So in conclusion, where are we headed? Some of the next, in terms of the package itself, we're interested in doing some more benchmarking against other algorithms written in Julia and other languages. We're also very interested in efficiency. Like Tucker, we're interested in systems that have very limited computational power, in particular CubeSats are some of our motivating examples. We're also very kind of excited about the new announcements in Julia 1.3 and the kind of the dawn or better parallelization, and we're very excited about leveraging that. And kind of returning back to the motivating problem that we opened up with, our lab is looking at digging into this area of contact and how do we take this very canonically difficult problem of contact interactions with the environment and kind of solve this from an principal optimization perspective and leverage the structure of the solver in order to tackle these problems. So in conclusion, we presented trajectory optimization is a powerful method for controlling dynamical systems, as well as TrajectoryOptimization.jl, which is a new Julia package that has state-of-the-art performance, as well as we believe to be a pretty intuitive and easy-to-use interface. As well as ALTRO, which is a new solver written from the ground up completely in Julia with very competitive performance. And kind of what this allows us to do is kind of shift the paradigm and now tailor the optimization solver to the problem that we're trying to solve, which kind of opens up a whole new suite of possibilities in terms of the problems we can solve and the solutions that we can get out of them. Thank you very much.
We have time for maybe one super quick question. Anyone? Sure.
Hi, I'll just repeat my earlier question. Do you foresee a need for MATLAB Simulink or something similar, and is there such thing in development?
As far as Simulink, I don't think anything exists yet as far as like the kind of the natural, easy to use like pipeline. But we've been leveraging a lot of like the dynamical results from the Julia Robotics community, the rigidbodydynamics.jl, and then their visualizer can kind of make that easier. And so we're kind of tackling the control side of the simulation environment where we have a simulation environment or a model and we want to control it. So that's kind of the perspective that this package is filling.
Let's thank the speaker.